What if everything you know, your memories, your future plans, even your sense of now, is just an illusion woven by something deeper? What if time doesn't actually flow and space isn't empty? What if reality as we know it is merely a shadow on the wall of a higher dimensional truth? This is not science fiction. This is modern physics. From ancient philosophers to black holes, quantum entanglement to time travel, join us as we unlock the true nature of the universe's most mysterious dimensions, space and time. Before there was time, there was nothing. But what is nothing? And what does it mean for something to be somewhere? These aren't just questions for philosophers in robes or scientists in labs. They're questions that define the very fabric of our existence. Welcome to our journey, a deep dive into the mysteries of space and time, the invisible threads that weave together our entire universe. But before we leap into the realm of quantum fields and relativity, we must go back, far back, to where it all began, with the human mind trying to understand its place in the cosmos. Before equations, there were stories. And before science, there was mythology. In ancient cultures, the concepts of space and time were often intertwined with deities and cosmic narratives. The Babylonians saw time as a cyclical process governed by celestial rhythms, the sun, moon, and stars forming a giant cosmic clock. In Hindu cosmology, time is eternal, flowing in immense kalpas, cycles lasting billions of years, echoing strangely with modern cosmological timescales. In Norse mythology, the world was built from the body of the primordial being Ymir, with the sky fashioned from his skull. Space was a sacred architecture, a structure with meaning, boundaries, and order. In these early civilizations, space was not empty, and time was not linear. Both were alive, divine, breathing, cyclical, and interconnected with life and death. But then came the philosophers. In ancient Greece, the pursuit of knowledge began shifting from mythology to reason and observation. Plato, in his famous work Timaeus, proposed that time was created simultaneously with the heavens, a moving image of eternity governed by celestial motions. For Plato, space was the receptacle, a kind of invisible matrix in which all things take form, the nurse of all becoming. He saw it as a third kind of reality, neither physical nor purely ideal, but something between. Aristotle, Plato's student, had a different take. He rejected the notion of an empty void. For him, space was not independent. It was defined by the position of objects in relation to each other. Space was the place something occupied, and nothing more. Time, for Aristotle, was simply the number of movement in respect of before and after. In other words, time doesn't exist without change, no time. This philosophical disagreement would echo through the centuries. While Plato and Aristotle shaped the mainstream Greek worldview, the atomists, like Democritus and Leucippus, argued something radical: that all matter is composed of indivisible atoms, and these atoms move through empty space, the void. To them, the universe was infinite, space was absolute and real, and motion required emptiness. This clash of ideas, void versus no void, infinite versus finite, absolute versus relational, would not be settled for 2 millennia. Fast forward to the 17th century, the birth of the scientific revolution. It was here that two titanic minds came into conflict over the very nature of space and time. Sir Isaac Newton, father of classical mechanics, saw space and time as absolute. In his famous words, "Absolute, true, and mathematical time, of itself and from its own nature, flows equably without relation to anything external." In Newton's view, space was a fixed stage, a container in which the universe unfolds. Whether anything existed or not, time would still tick, and space would still extend. But Gottfried Wilhelm Leibniz, a German polymath and philosopher, strongly disagreed. He claimed space and time were relational, not real things on their own, but systems of relations between objects and events. Without matter, there is no space. Without change, there is no time. Leibniz challenged Newton with the principle of sufficient reason, the idea that nothing exists without a reason. Why should the universe be located here rather than there, or now rather than then, if space and time are absolute? This philosophical argument spilled over into mathematics and physics, eventually influencing the structure of relativity centuries later. In the 18th century, Immanuel Kant offered a radical synthesis. He proposed that space and time were not properties of the external world at all, but rather forms of human intuition. According to Kant, space and time are not things in themselves. They are the a priori conditions of our perception, the lenses through which we experience the world. In simple terms, space and time are the mental scaffolding that allows us to perceive anything at all. We cannot imagine experience without them. They're hardwired into our cognition. Kant didn't deny the external world, but he claimed we could never know it as it truly is, only as it appears through the filters of space and time. This idea, that reality may be radically different from our perception of it, would later be echoed in quantum physics. By the 18th and 19th centuries, the Newtonian worldview dominated science. The universe was seen as a vast clockwork machine, governed by fixed laws of motion in absolute space and time. The success of Newton's laws in explaining planetary orbits, projectile motion, and tides was breathtaking. But this picture also came with a profound implication: determinism. If we knew the position and velocity of every particle in the universe, we could predict the future with perfect accuracy. Time was like a railroad track, unbending, universal, and inescapable. This mechanistic vision fueled not only science, but also philosophy, economics, and politics. But there were cracks in the gears, puzzles that Newtonian physics couldn't explain. Chief among them, the speed of light and the mysterious behavior of electricity and magnetism. The stage was set for a revolution. In the 19th century, scientists like James Clerk Maxwell began unifying electricity and magnetism into a single framework, giving rise to electromagnetic waves, including light. But there was a problem. Light always seemed to move at the same speed, regardless of the observer's motion. This defied Newtonian logic. To solve this, physicists proposed a strange substance called the luminiferous ether, an invisible medium through which light waves traveled. But when experiments like the Michelson-Morley experiment, 1887, failed to detect this ether, it shook the foundations of classical physics. If there's no ether and light doesn't change speed, what's going on? The answer would come from a young patent clerk in Switzerland, but that's a story for the next chapter. Imagine standing on a train platform. A lightning bolt strikes the tracks ahead, but someone on a speeding train sees it differently. Who's right? In Einstein's world, both are. Because time isn't absolute, it's relative. Welcome to the revolution that changed everything. At the dawn of the 20th century, space and time were treated as separate entities. According to Newtonian physics, space was a static stage, an unchanging backdrop, while time ticked forward uniformly for all observers. But this comforting view was about to be upended. In 1905, a young patent clerk named Albert Einstein published his theory of special relativity. It showed that space and time are deeply interconnected. The faster you move through space, the slower you move through time. This wasn't just theoretical. It was mathematically provable and eventually experimentally verified. Key consequences of special relativity: time dilation. A moving clock ticks more slowly than a stationary one, proven by observing the decay of high-speed muons and precise atomic clocks on satellites. Length contraction. Moving objects contract in the direction of motion. Relativity of simultaneity. Events that appear simultaneous to one observer may not appear so to another moving at a different velocity. Einstein's insight was not just about physics, it rewired our very notion of reality. Space and time weren't separate. They were merged into what physicist Hermann Minkowski called space-time, a four-dimensional continuum. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows. Hermann Minkowski, 1908. Einstein didn't stop there. In 1915, he introduced general relativity, a theory of gravity that replaced Newton's force with geometry. According to Einstein, mass and energy curve the fabric of space-time, and that curvature tells matter how to move. This idea was radical. Gravity wasn't a force pulling planets, it was the warping of space-time itself. Key predictions of general relativity: gravitational time. Dilation. Time runs slower in stronger gravitational fields, confirmed by clocks placed at different altitudes on Earth and by the GPS system. Bending of light. Light follows the curved path of space-time, verified during a 1919 eclipse when starlight bent around the sun. Black holes, regions where space-time is curved so intensely that nothing, not even light, can escape. Gravitational waves, ripples in space-time caused by violent cosmic events, first directly detected by LIGO in 2015. General relativity not only matched Newton's predictions where they overlapped, it also made new ones that Newton's framework couldn't. It became the gold standard for understanding the large-scale structure of the universe. Einstein's theories also transformed our understanding of time itself. There is no single universal now. Each observer carries their own clock, and those clocks can run at different rates depending on velocity and gravity. In this framework, past, present, and future all exist in a four-dimensional block called the block universe. According to this view, time doesn't flow. We simply experience it slice by slice. The distinction between past, present, and future is only a stubbornly persistent illusion. Albert Einstein. But this notion, while mathematically elegant, poses deep philosophical questions. Why do we experience time as flowing if physics says otherwise? What determines the arrow of time? How does consciousness fit into this model? While Einstein was rewriting gravity, other physicists were revolutionizing our understanding of matter and energy on the smallest scales. Quantum mechanics, developed between 1900 and 1930 by scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, introduced a world where particles can be in superposition, existing in multiple states at once. Outcomes are governed by probabilities, not certainties. Observation appears to collapse possibilities into actual events. Particles can be entangled, instantly influencing each other over vast distances. At this quantum level, space and time become fuzzy. Time evolution in quantum mechanics is handled by the Schrödinger equation, which seems to treat time as external and absolute, a conflict with relativity. This clash between quantum mechanics and general relativity is the deepest rift in modern physics. To bridge relativity and quantum mechanics, physicists developed quantum field theory, QFT, the most successful framework in physics. In QFT, particles are excitations of underlying fields that permeate space. Space is not empty. The quantum vacuum teems with activity. Virtual particles blink in and out of existence due to uncertainty. In QFT, space is a dynamic, energetic sea, and yet, time is still treated separately, creating an awkward tension. Attempts to merge QFT with general relativity, to create a quantum theory of gravity, remain incomplete. What happens to space and time at the Planck scale, the smallest scale of the universe, where quantum effects dominate gravity? Several competing theories try to answer this. Loop quantum gravity. proposes that space-time is made of discrete loops, like tiny atoms of space. Time might not be fundamental, but emergent, arising from deeper, timeless laws. String theory suggests that particles are tiny vibrating strings. Space and time may be manifestations of the underlying string dynamics. Extra dimensions beyond our perception may be curled up tightly. Causal dynamical triangulations build space-time from fundamental simplices, geometric building blocks. It recovers smooth space-time from quantum rules without assuming it exists from the start. All of these theories challenge the idea that space and time are continuous. Instead, they may be quantized, emergent, or even illusions. One of the most radical ideas in modern physics is that space-time may arise from quantum entanglement. Physicists like Juan Maldacena and Mark van Ramsdonk propose that the geometry of space-time is built from entangled quantum bits. In this view, more entanglement equals stronger geometric connections. Breaking entanglement equals tearing the fabric of space. The phrase ER equals EPR sums this up. It suggests that Einstein-Rosen bridges, wormholes, are equivalent to EPR entangled pairs. That is, geometry and entanglement may be two sides of the same coin. If true, this would mean that space itself is not fundamental, but built from information. If space can emerge from entanglement and quantum bits, can time also emerge? Some researchers believe time may be an emergent illusion, arising from correlations between quantum states. Others suggest time is just a parameter we use to describe change, not a real, flowing entity. The concept of a timeless universe, where all moments exist simultaneously, is deeply counterintuitive, but mathematically consistent. Even in Wheeler-DeWitt equation, a proposed unification of quantum mechanics and gravity, there's no time variable at all. The universe, in its most fundamental description, may be frozen. But if time is emergent or illusory, why do we experience a past and a future? The answer may lie in entropy, a measure of disorder. The second law of thermodynamics says entropy tends to increase. This creates a thermodynamic arrow of time pointing from order to disorder. We remember the past because it was more ordered. The future is unpredictable because it's more disordered. In this way, the arrow of time may be a consequence of initial conditions, not of fundamental physics. Not only is the universe stranger than we imagine, it is stranger than we can imagine. J.B.S. Haldane. As we reach the frontiers of scientific understanding, the smooth, continuous fabric of space-time envisioned by Einstein begins to fray. General relativity has proven remarkably successful in describing gravity and large-scale cosmic phenomena, yet it breaks down at extremely small scales, the so-called Planck scale, where quantum effects dominate. Here lies the domain of quantum gravity, an arena where two titans of physics, general relativity and quantum mechanics, must be reconciled. Several competing theories attempt to unify these frameworks. Loop quantum gravity, LQG. LQG suggests that space-time is not smooth, but quantized. Imagine space as a fabric woven not from threads, but loops, tiny discrete packets of area and volume. These loops, called spin networks, evolve over time into spin foams. LQG eliminates singularities, suggesting a bounce instead of a big bang, a cyclic view of the universe. String theory. String theory posits that all particles are tiny, vibrating strings, and their modes of vibration determine mass and charge. But string theory doesn't stop there. It suggests the existence of extra dimensions, typically 10 or 11 in total. These dimensions are curled up in geometries known as Calabi-Yau manifolds. While still unproven, string theory offers a mathematically consistent path to unify gravity and quantum mechanics. Causal dynamical triangulations, CDT. This approach models space-time as composed of discrete, triangular building blocks, evolving in a causal manner. Over time, these triangles grow into a continuum-like structure, resembling the classical spacetime we observe. CDT gives rise to spacetime from simple geometric rules, much like fractals in nature. One of the most mind-bending ideas of modern theoretical physics is the holographic principle. Proposed by Gerard 't Hooft and expanded by Leonard Susskind, it posits that all the information contained in a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a hologram. This idea found strong support in string theory, especially in the ADS-CFT correspondence by Juan Maldacena, which describes a relationship between a gravitational theory in a higher dimensional bulk and a quantum field theory on the lower dimensional boundary. The implication? Our perceived 3D universe might be a projection. Space-time itself could be emergent, arising from entanglement patterns in underlying quantum systems. This is not just philosophical musing. Researchers like Mark van Ramsdonk have shown how quantum entanglement could glue space together. In the quantum realm, time becomes deeply paradoxical. Consider the delayed choice quantum eraser experiment. In this setup, a photon can behave either as a wave or a particle, but the decision to observe its path can be made after it has passed through the slits. Even more bizarrely, this choice seems to retroactively determine the photon's past behavior. This leads to speculation about retrocausality, the idea that effects might precede causes. While not yet mainstream, retrocausal models are gaining traction among researchers attempting to explain quantum correlations without violating relativity. Time in quantum mechanics doesn't flow. Instead, it's treated as a parameter, unlike other variables which are quantized. This creates a tension between our intuitive understanding of time's arrow and the time-symmetric laws of quantum physics. Why does time move forward? The laws of physics are time-reversible, yet our lived experience, from aging to entropy, reveals a clear arrow of time. The answer lies in the second law of thermodynamics. In a closed system, entropy, disorder, always increases. The early universe began in a state of low entropy, enabling complex structures and the emergence of time's arrow. Yet the deeper question is, why did the universe begin in a low entropy state? Some suggest it's due to cosmological inflation flattening the universe, while others believe it's tied to deeper laws we have yet to uncover. Roger Penrose introduced the concept of Weyl curvature hypothesis, suggesting that the Big Bang had zero gravitational entropy. As the universe evolves, gravitational clumping increases entropy, establishing a temporal direction. Time may be statistical, not fundamental, a macroscopic illusion emerging from microscopic chaos. Time travel has long fascinated physicists and science fiction writers alike. Solutions to Einstein's equations, such as Gödel's rotating universe and Tipler cylinders, allow for closed time-like curves, CTCs, where time loops back on itself. Wormholes, too, might serve as cosmic shortcuts, if they can be stabilized by exotic matter. But time travel poses paradoxes, the infamous grandfather paradox, for instance. Some resolutions lie in many worlds interpretation, MWI, where each decision branches into a separate universe, preserving consistency across timelines. The multiverse. Inflationary cosmology suggests that our universe might be just one of countless others in a multiverse, each with different physical laws. String theory's landscape contains 10 to the power of 500 possible vacuum states, a cosmic jungle of possibilities. Some physicists, like Sean Carroll, argue that time might emerge differently in different branches of the multiverse. In some, it could flow backward. In others, it may not exist at all. Emergent time. Recent approaches suggest that time is not fundamental, but emerges from the entanglement of quantum states or thermodynamic interactions. In Carlo Rovelli's Relational Quantum Mechanics, Time is a relationship between interacting systems, not an external backdrop. Similarly, Julian Barber argues in The End of Time that the universe exists as a collection of nows, timeless configurations. Change is illusion. Time is a story we tell. We are far from a final theory of space and time. Every discovery opens new mysteries. What is the fabric of reality? Why does time flow? Is space-time emergent or fundamental? As we explore these questions, we stand on the brink of a paradigm shift. Much like Copernicus dethroned Earth from the center of the cosmos, the next revolution may dethrone time and space from their foundational status. To understand the universe, we must first understand how we understand, and that may be the ultimate voyage. Time is an illusion, lunchtime doubly so. Douglas Adams. If this journey into the secrets of space and time expanded your mind, imagine where the next episode could take you. Subscribe and hit the bell icon to never miss an episode of mind-bending science. Drop your thoughts in the comments. Do you believe time is real? Or is it just a human invention? And don't forget to share this with someone curious about the universe. Until next time, keep questioning everything.